The name of my talk is Squeeze More Juice, and we'll be squeezing juice from our CI system. All right, quick intro. I am Sergey. I work for Uber, obviously. If you see people with badges, but like that, but no stickers, it means that they're from Uber. I am a tech lead for DevTools space at Uber. So I manage pretty much everything that is about developer productivity and making people productive. All right. So what's the problem? The problem is AI is a problem, apparently. With AI, it starts so easy to create code changes, that people started to create them en masse. And these changes also quite big and complex. The number of lines per change also grew up. The thing is that we practice monorepo doesn't help, because every single code change we validate across all of the services, across all of the tools, and we spend a whole ton of capacity on that. So we start to pay more money for machines, and we've decided that it's a little bit too much, and we probably want to optimize the way how we run our builds on CI machines. So what's a traditional approach to this problem? Traditional approach to this problem is to try to understand if the build is big or not, big or small, in the process called job sizing, and then allocate that build on a specific machine or specific container that has a specific set of dedicated resources. Resources like number of CPU cores, some RAM, and some disk. The problem with this approach is typically these jobs are sized for their peaks. If you know that a specific job at its peak needs 100 gigabytes of RAM, then we need to allocate it to a machine that has 100 gigabytes of RAM allocated for it. However, it's very rarely the case that the job needs this 100 gig of RAM for a duration of its run. It may need more, it may need less, but in order to execute the build, we have to allocate for peaks. As a result, if you compute the average utilization of RAM or CPU, you'll notice that these machines are very underutilized. For example, our CPU utilization for CI machines aggregated over weekends and off-peak hours was like 12%, very low. So Uber approach is a little bit different than that. So Uber puts more jobs on a physical machine with one single premise. These peaks of utilization, they very rarely collide. So let's say if we run 2 build jobs on the same machine and we give it pretty much all the amount of RAM that they could use. Whatever it can claim from the machine is going to be used for the job. We call this strategy overcommitment, which means that if you schedule 10 jobs on a single machine and each job needs 100 gig of RAM, but we have only 300 gig of RAM, then if these RAM consumption peaks collide, we're going to have a problem, but they rarely collide. So we are able to execute more builds on the same physical machine and thus use just less machines and overall increase our utilization. All right, now what if multiple peaks do collide? If some jobs require more CPU power, that's typically okay, because the operating system scheduler is, in most cases, smart enough to just delay the execution of certain threads and still complete the job. The problem is typically RAM or disk, and I'm going to talk about RAM. Like I said before, what happens if 2 jobs require more RAM from the machine at the same time than machine can provide. The job is killed. With killer, we don't use page swap files, so the job basically just ceases to exist. What's our answer to that? Our answer is to still overcommit, but provide a number of safety nets. The very first safety net that we do is, surprise, a retry. We have a Bazel wrapper, and the Bazel wrapper detects if Bazel exits with exit code, and if so, it retries the job on the very same machine, and the job uses pretty much same accumulated artifacts in a build folder on the same machine and typically completes fast. We started to observe when we put a number of jobs on a physical machine, a number of expensive jobs. When we start to put 2 or 3, we start to observe that. And it fixed the issue. The next use case is a little bit more interesting, and that's a war story I wanted to share with you that we just experienced when we started to put even more jobs on a single machine. The jobs start to time out, but surprisingly, we found that they time out only when they all execute a lot of Go-link actions. So a typical Go build, it first compiles pretty much same as a C compilation. It first compiles the code into so-called Go archives, and then the final step, very expensive, a linker that links all together into a single executable. So we run multiple targets on the same machine, multiple builds, and as a result, it may happen that multiple Go-link targets execute at the very same time. And when they do, we notice that the job may just suddenly time out, 30 minutes. We retry the job on a fresh machine or even on the same machine after that, and it surprisingly completes in less than 2 minutes on the very same revision with the very same inputs. So it took us a while to understand what was going on there. We noticed that it was a very high I/O load on a disk, and first we thought, hey, maybe that's I/O contention. But apparently it wasn't. Apparently it was still RAM. So we root caused the problem into the way how linker manages memory. And it doesn't use malloc, it uses mmap. So it mmaps a disk space, which is a Go archive, into the memory. And because it does so, the actual read from the disk into the RAM happens when Go linker needs to read something from Go archive. And because we have so many and so big Go archives, it starts to read and then evict of these pages. During that, this condition is known as a page fault storm or a mmap thrashing. And apparently the disk might be read into RAM multiple times throughout the same build. Why killer didn't kill the build? Well, because this memory, mmap memory, is considered as reclaimable by the kernel. And that means that instead of just halting the build, kernel starts to evict pages. But kernel has no whatsoever knowledge when the specific page is used or when it's not used, so it just evicted them. And the next time the linker needs that page, it will be materialized back into the memory. So very interesting. RAM apparently is the problem, but we had whatsoever no indication that RAM was a problem. So the solution is another safety net that we've put over it. We call it Paralink. So Paralink is basically a gate, a tiny wrapper built on top of the linker. The wrapper checks specific counters on the machine, a number of page faults. And if it sees that the number of page faults is high, it doesn't allow Go-link process to proceed. It basically slips it, delays it up to a certain time, and then it rechecks these counters again. So it allows only certain amount of Go-link processes to be executed at the same time, not thrashing the machine. The wrapper is pretty fast, written in Rust, and integrated into Bazel's toolchain. We just aim to have it with no overhead. This is pretty much it. I just wanted to share this war story, which I think is pretty interesting. The name of the talk was how to overcommit and face no consequences. And I think I lied, because you will face consequences. However, just by doing what we do, we were able to save at least 1/3, 30 to 35% of the capacity that we would be using otherwise, and it's thousands of machines, a lot of money. So you can't avoid consequences, but you can fight them efficiently. That's it. Thank you.